Welcome back to 3 Inquisitive Kids. Today we're going to learn about the Epsilon-Delta definition of a limit. We're going to be answering 3 main questions in this video. What is a limit? How do we find limits? And the Epsilon-Delta definition. So these first 2 questions are going to be really brief and they're going to be quick, introductions or recaps of the basic concept of a limit. The main thing we're going to be focusing on today is the third topic, which is the Epsilon-Delta definition. So let's first start with the first question. What is a limit? Well, a limit is just the value of a function when its x value is infinitely close to a certain number. For example, on this graph, we have the function f of x. So the limit of f of x when x is infinitely close to, let's just say, 1 is what? How can we find the limit of f of x when x is infinitely close to 1? Well, essentially, this question is asking, on this graph, when we zoom really close to the point where x is equal to 1, what is its corresponding y value? Which means, as these 2 arrows are meeting, what value on the graph are they getting really close to? Well, you can see that value is 1. So the limit of f of x as x approaches 1 is equal to 1. So here we're using a very important concept that we're going to come back to later, which is infinitely approaching. So here we're just saying that x is super close to the value 1, but is not yet reaching the actual value of 1. So you can think of this as 0.99999, an infinite amount of 9s, but it will never really approach 1. So this is the basic concept of a limit. Now, how do we find limits? Well, let me give you another example. Now, all functions look like this. For example, sometimes it looks like this. You'll see that there is a gap, right, in the function, and on this specific point, it has a different value that is special from the rest of the function. So it is not equal to the pattern. So in this case, what would be the limit of f of x when x approaches 1? Well, some might say, isn't it 2? Because the value of this point is 2. Well, that's wrong. Because remember, we're not trying to find the value of the function on this point. We're trying to find the value of the function, or at least the value that it approaches to, when the x value is super close to 1, but not yet really 1. So we're looking at these 2 sections here. Like, what is it infinitely approaching to? Well, it's still approaching 1. This is still our answer, because it is not yet really on that point. It is just really close to that point. So this is just another type to be careful of when trying to find limits. Finally, there's also this other scenario where the function seems to be breaking. So there's a complete break, and there is a complete break, and if you look from the left or from the right, they don't really meet. It's kind of broken apart. It's kind of split. So that is when there is no limit, because if you approach it from the left and if you approach it from the right, they will end up having different values, which means that there really is no limit that exists for that value. But all of that aside, let's take a closer look into the Epsilon-Delta definition. What is the Epsilon-Delta definition of a limit? Well, it is basically just another way to answer the first question. This is a full circle to our first question, which is what is a limit? because this is the more clear, scientific, and mathematical precise definition of a limit. And we're going to be using the concept of infinitely approaching. Now let's dive deeper into the epsilon-delta definition of a limit. Here we see a graph of the function f of x, and this is the visual of this limit right here. So we're saying that the limit of the value of f of x as x approaches a, and yet you'll see that a is an x value here, is equal to L. So we're just describing this point right here. The value of f of x when x approaches a is equal to L. So how can we really define this though? How do we prove that that this is its limit? Well, here is the strict definition for it. And I'm going to first read it aloud, but don't worry, we're going to break this down step by step afterwards. For every epsilon that is greater than 0, there is always a delta that is greater than 0, such that 0 is less than the absolute value of x minus a, which is less than delta, and the absolute value of f of x minus L is less than epsilon. So how does this define a limit, and what does it really mean? Well, the first step is to understand what epsilon and delta really mean and their representations visually. So here we have this. E, this looks like an E. This is really epsilon. It's a Greek letter that in this case is being used to represent error. And delta is another Greek letter that is being used to represent difference. You may have seen delta being written like a triangle before. That is because that is the uppercase, a way to write this. This is the lowercase. So this is just what epsilon and delta mean as Greek letters. And visually on the graph, how are they being represented? Well, as you can see, here we have delta on the x-axis and epsilon on the y-axis. So here is A, and delta is basically the distance from A, so a little difference between x and A. Because here we're really saying when x approaches A, right? That's the value, that's the limit right here. So when x is slowly approaching this point, x will be super duper close to A, but there's always going to be a little difference between x and A. It's approaching A, but not quite there yet. At the same time, when x is approaching A, the value of f of x as a function on the y-axis is also slowly starting to get closer to L, which is what the f of x is approaching but not quite reaching. Delta is always going to measure the difference between x and A, and epsilon is always going to be measuring the distance between L and the actual value of f of x. So I hope that clears it up a little bit. If not, you could go back and rewatch, or you could just ask a question in the comments down below. But now you know what epsilon and delta represent. Let's go back into this definition right here. So here we have a symbol, and this symbol just means for every. So the first line is all about defining these two variables, epsilon and delta. So this is saying for every epsilon that is greater than 0, there is always, this thing here represents there is always. So for every epsilon that is greater than 0, there is always a delta that is greater than 0 as well. So it's just setting these two variables, epsilon and delta. For every epsilon that is greater than 0, delta is greater than 0. And these two variables satisfy the following condition. So what does this condition say? So here, what does x really represent? Well, x is approaching A, but not quite reaching A. So the difference between x and A, right, we're taking their absolute value. So the distance between x and A is always going to be greater than 0, but less than delta. And delta can be infinitely small. So delta could be as small as you want it to be, but there is always going to be a smaller value. The difference between x and a is just describing how x is slowly approaching a but not quite there. It's less than delta, but always greater than 0. This also causes the value of f of x, which is basically the y value, to approach L, but is always going to be less than epsilon. So f of x is approaching L, but it will always be greater than 0 and less than epsilon. So this entire thing is just describing how while the value of the function can get as close as you want to the limit, can keep getting closer and closer, but it will never really reach that limit. Now that is basically the epsilon-delta definition of a limit, and now let's talk about some ways we can use it and apply this when solving certain problems. Now with our understanding of the epsilon-delta definition, let's use that to prove some limits. So our first problem is to prove the limit of 5x minus 6 when x is approaching 2 is equal to 4. So essentially the question is saying, if we were to use the epsilon-delta definition, what value can we give delta to make both of these conditions true? The first condition is the delta condition, and the second condition is the epsilon condition. The first thing we can do is to substitute 4 into what we know, and 2. So we know that when x is approaching 2, right? So in this case, a is equal to 2. So we know that x minus, actually I'll use a different color, 2 is less than delta. And that 5x minus 6 minus L, which in this case is 4, is less than epsilon. Both of these conditions have to be true. But we can continue simplifying this right one into 5x minus 10 is less than epsilon, which we can simplify again and turn into 5 times x minus 2's absolute value is less than epsilon. So now, as you can see, for each of these inequalities right here, we are using x minus 2. So that's where we can start. Because we know that x minus 2's absolute value is already less than delta, it means that 5 times x minus 2's absolute value will have to be less than 5 delta. So we can change epsilon into delta times 5. So here's what we can do next. Given that epsilon is greater than 0, we can set delta as epsilon over 5. Remember, delta can be any number that we want it to be. So all we have to do is set delta to a value, which is epsilon divided by 5. So if this first case is true, if this first condition is true, then it will also cause the second condition to be true as well. Therefore, if 0 is less than the absolute value of x minus 2, which is less than delta, we know that 5 times x minus 2 will be less than 5 times delta, but since delta is already equal to epsilon over 5, we could write it as 5 times epsilon over 5, which is just equal to epsilon. So as you can see, because we set delta as epsilon over 5, we automatically made it so that once the first condition was true, the second condition is true. So when proving limits using the epsilon-delta definition, the key is to see what value can you set delta as in order to make both of these conditions true. So I'm going to write that down right here. What can we set delta as to make both conditions true? To make both conditions true. So here is how we prove that the limit of this function is equal to 4. Now let's try another problem. Now we're being asked to prove this is true. And we're being asked to prove that the limit of the function 7b plus 2 is equal to 37 when b is approaching 5. So again, we have to be asking ourselves the same question. What can we set delta as to make both of these conditions true? And I'm going to copy this over here as well. So as you can see, delta is any variable. So we can set delta to any value that we want it to be. The first thing is to write down both of these two conditions. So these are the two conditions that we want to be true. When, in this case, instead of x as the variable, b is the variable. So that's what we'll use. 0 is less than the difference of b and 5, which is less than delta. And the second condition is that the value of f of x, which in this case is 7b plus 2, so 7b plus 2 minus 37, which is L, is less than epsilon. So what does D equal? This is what we're trying to find first. Well, let's see if we can simplify condition 2 a little bit more. We'll see that this is equal to 7b minus 35 is less than epsilon, which is equal to 7 times b minus 5 is less than epsilon. Well, here we have a b minus 5, and here we also have a b minus 5. So this is where we're going to compare them. So because 0 is less than b minus 5, which is less than delta, and 7 times the absolute value of b minus 5 is less than epsilon, we know that if we multiplied 7 on both sides of the first condition, this will turn into 0 is less than 7 times b minus 5, which is less than 7 delta. So let's set, because here they have the same value, let's set delta as epsilon over 7. So if we set delta as epsilon over 7, this will automatically be true, right? Because if you replace 7 times delta with 7 times epsilon over 7, this will cancel out and give you epsilon. So this immediately goes back to our original definition, and if this satisfies the definition of a limit, then it means that this is indeed the limit to this function, and we have proved that this is a limit. So that is all for today's video, and we'll see you in our next video.